So we have this molecule with a chemical formula of C4H6, and this is called butadiene, and it's called but because there are 1, 2, 3, 4 carbons, and it's a diene because there are 2 double bonds. And this molecule has a cool property in that it can actually react with itself to form C8H12, and that looks something like this. So we have 3 double bonds, and it has 8 carbons, so this is an octatriene, and you might even say 2, 4, 6 octatriene, just to be specific. And we should balance this equation because that is what good chemists do. So let's put a 2 in front of this because it requires 2 of these to make 1 of these. And let's say we want to study the rate of this reaction. So to study the rate of this, the rate or the kinetics, let's compare some data. So this reaction can happen in the gas phase. So we can talk about these rates in terms of concentrations, but we can also talk about them in terms of partial pressures. So let me go ahead with labeling this graph. So let's say negative D partial pressure of C4H6 over dt. Again, this is the rate, and we're going to compare that to the partial pressure of C4H6. Now, the reason that we can do this is that we have this formula, very useful formula, which says P times V equals nRT. And so we can rearrange this to get pressure by itself. So we get nRT over V equals P. And now I'm going to circle this part of the equation. So here we have the number of moles over the volume, which is another way of saying concentration. So we can rewrite this again as P equals the concentration, and I'm going to abbreviate that as big M for molarity times RT. So pressure is directly related to the concentration or the molarity by the gas constant R and the temperature T. So we can talk about these reactions and their rates in terms of partial pressures if we're dealing with gases. That's why here I'm comparing the rate of consumption of C4H6 to the partial pressure of it. So let's say we have a partial pressure of 1, and we have a rate of 1 associated with that. The units don't really matter right now. And then let's say we run this experiment again, except we have a partial pressure of 2. Now the rate goes all the way up to 4. So we started from 1, 1, and went up to 4. And then let's say we run it again using a partial pressure of 3. And now we get a rate all the way up here at 9. So what this begins to look like, it sort of looks like a squiggle here, but it's supposed to look like a quadratic. And just as a reminder, quadratics have the form of y equals x squared. They can have other stuff, but x squared is the highest power. When we have a reaction where changing the pressure or concentration of the one reactant causes sort of squared change in the rate of consumption of that reaction, this is what we call a second order reaction. Now, just to sort of confirm our data findings here, let's do another sort of comparison. So this time, let's compare the partial pressure of C4H6 to the time that has passed. Again, the units don't really matter right now. So if we did this, we would get some sort of curve like this. This isn't too useful for us. What is more useful is if we say 1 over the partial pressure of C4H6. Now, if we draw a graph comparing this to the time that has passed, what we get is a straight line like this, with slope equaling our reaction constant K. This is also consistent with second order kinetics. So this is also consistent with second order kinetics. Because this is second order kinetics, we have some rate laws associated with it. So first we have our differential rate law. And the differential rate law says that our rate, negative D partial pressure of C4H6 over dt, is equal to K times the partial pressure of C4H6 squared. Now again, we could have done this in terms of concentration, but as I showed you up here, the pressure and concentration are related to each other, and it is good to be able to do this in terms of partial pressures. So this is the relationship that we can use, and it would, if we wanted to do this in terms of concentrations, it would just be concentration of C4H6 here and concentration of C4H6 squared here. So in addition to our differential rate law, we also have an integrated rate law. And what our integrated rate law says is that 1 over the partial pressure of C4H6 is equal to the rate constant K times T. Now we should put a T here. So this is the partial pressure at some time T. So this is 1 over that partial pressure, is equal to the rate constant K, which is again derived from our slope here, times T, plus 1 over the initial partial pressure of C4H6, which I am labeling with a 0 or initial. So this is our integrated rate law, and now let's see how we can get our half-life. And just as a reminder, half-life is often abbreviated as T1/2. So that's defined as the time that the partial pressure of C4H6 at that T1/2 is equal to 1/2 of the initial partial pressure of C4H6. So substituting this into our integrated rate law, what we get is 1 over 1/2 P C4H6 initial, because again, this is the partial pressure at this given time, equals K times the half-life T, because that is the time that we're comparing this to, plus 1 over the initial partial pressure of C4H6. And so now we set about solving this. So this term here is equal to 2 over the partial pressure of C4H6 initially. That's equal to K times T1/2 plus 1 over the partial pressure of C4H6 initial. So I'm going to bring this term here over to this side of the equation. So what I do is just subtract it from this side. So we get 1 over the partial pressure of C4H6 initially is equal to K times our half-life, T1/2. And then we just divide both sides by K to get our half-life. So T1/2 is equal to 1 over K times the partial pressure of C4H6 initially. So this is our half-life equation, and again, I could have done this in terms of concentration, but because we're dealing with gases, and for gases, the pressure and concentration are related, so here I have it in terms of partial pressure, but we could have had it in terms of concentration. So this is our half-life, and here is our integrated rate law equation. And then finally, we have our differential rate law equation. And so just to sort of conceptualize these equations, so what this half-life equation here tells us is that if we increase the initial partial pressure of C4H6, or the initial amount of this, our half-life actually gets smaller. So it takes less time to reach the half-life the more of this reactant we have. And that sort of makes sense in terms of the collision theory. The more of something there is, the more frequently they'll collide, especially if it's just reacting with itself. So that's how the half-life sort of functions, and then the differential rate law, if we increase the amount of our starting reactant, our rate will increase at a squared rate of that. So what I should say is, like, if we double the partial pressure, we square that double, so we actually quadruple the rate.